Okay, so I'd like to start by thanking the audience for inviting me to this workshop. It's very nice. Okay, so I will talk about something exact and something two-dimensional. So I fit in the line. So this part of it is partly based on work done in collaboration with my ex-student Sylvia. And basically, I mean, this is some very technical paper where we take this something called JTbar deformed CFT, study to their symmetries from all sorts of perspectives, and then we do a precision holography, which is another like nasty calculation, but everything matches perfectly. So it's some hardcore thing. I thought I wouldn't kill you with all these technical details here, but spend instead most of the time trying to relate this work to Kerr CFT. Explain the status, as far as I see it, of the Kerr CFT correspondence, and also try to explain why I think holography is sort of necessary in that context. Okay, so general motivation starts with this beautiful universal formula for black hole entropy, which strongly suggests that gravity is holographic, by which I mean it can be rewritten as a non-gravitational theory in one-dimensionless. And of course, we have this very beautiful realization of the holographic idea and like really precise realization of it in the ADS-CFT correspondence. There are really two approaches. So one is the top-down approach, the original approach through which it was discovered, where you take some string theoretical objects, have very different descriptions. You take a low energy decoupling limit, and this gives you a duality between specific, field theories and gravitational theories. And then what's very nice is that one can do precision tests with various precision tools. So that's one way to think about it. The other way to think about AD-CFT is bottom-up, whereby any CFT that satisfies certain requirements, large n, maybe large gap, should respond to some theory of gravity in some higher dimensional ADS spacetime. And then sort of the universal features of the CFT, their structure, is coded in the asymptotic geometry. So the CFT symmetries are asymptotic symmetries of the ADS spacetime. The correlation functions are related to scattering. Thermodynamics is encoded in black hole thermodynamics. And basically, we don't really care what the theory is in this approach. If you change a little bit the gravitational action, you're just going to be changing a bit the CFT spectrum of the couplings. But really changing the structure, of course, there's a good question if a CFT would those properties exist, but you're not changing the structure. So that's the general idea. What I'm interested in is going beyond the ADS-CFT, and this is kind of hard. So again, one can talk about top-down and approaches. Top-down is via string theory decoupling limits, and here the problem is that there are relatively few concrete examples where you really choose the asymptotics, so they may be weird. You might get flat space, but with a linear dilaton, and maybe we don't care. You get sort of disparate examples, and even if they come in families, I don't think they've been systematized, so we don't understand universality classes of asymptotics in these non-ADS holography of funny asymptotics. Now, oftentimes, these theories, like when you want to use supergravity near the boundary, they're going to be very highly, strongly coupled and non-local. So I have no clue how to track them down. An example is due to string theory. And also, the precise rules for holography are not understood in general in this background. There's some work, for example, for DP brains, but there's really no general understanding for these top-down examples. So what people do most of study non-ADS holography is bottom-up. And here the focus is different. Pick a spacetime that you like. You pick flat space, you pick de Sitter. I'll talk about warp state. There's another bottom-up. And because, for example, in these two cases, we need the decoupling limit from string theory that leads to them, so it's simply assumed there's going to be some sort of field theory dual. That's an assumption. And then it is assumed that, no matter what action you choose, you're going to get sort of the same universality class of theories. And then to infer the properties of disputative dual QFT from the spacetime. So it's the same symmetries are asymptotic symmetries, and so on. The problem with this game is these quantities can be ambiguous. Like the asymptotic symmetries of the space depend on the boundary conditions that you impose, but this is not something that you know. So even the entropy is ambiguous because that presumes knowing the relationship between your bulk time and the boundary time, and there's not something that you know. So there's actually a lot of ambiguities, and there's nobody telling you that, okay, there's some choices over here, that whatever answers you get from these are going to be logical, self-consistent. They're going to actually correspond to a theory. So that's a little bit, say, problematics of non-ADS holography. So what I'll do in this talk, I'll try to examine challenges of non-ADS holography with one example, which is the Kerr CFT. It's just an example which has a lot of problems, so it's. And as we'll see, it's a really important issue is that of boundary conditions. I think that's the main stumbling block. We don't know how to pick boundary conditions for this correspondence. And given this state of affairs, I'm going to argue that more input is needed, like independent input is needed in the holographic dictionary. Ideally, some knowledge of what the dual field theory is or what its properties are. And then I'm just going to produce some field theory that I think has the right flavor and develop for it. That's the JTbar story. And then try to see how this story is going to reflect back on Kerr CFT. So is the logic clear? Okay, so let me just briefly talk about Kerr CFT. So the Kerr CFT correspondence, I mean, one can say it's like an example of bottom-up holography. You knew nothing about the space-time, and then you come up with methods, asymptotic symmetries, and so on, and propose something. So what it does, so one looks at the very near horizon region of an extreme Kerr black hole. So this is known as the geometry. And its peculiar feature is that it contains a factor, and there's a U1 fiber over this ADS2 with a variable fiber size. This whole thing is known as warped ADS, either a squashing or a stretching of ADS, and then some other angle. And the Kerr CFT claim is, like the Kerr CFT set of ideas is that, you just come up with some boundary conditions on this geometry, which come out of nowhere, and then you find that you have sort of an infinite set of symmetries that enhance this U1 right. They form a Virasoro algebra with some central charge. And then you take the central charge, you stick it into Cardi formula for no particularly good reason, you get to reproduce the Becker-Stein-Hawking entropy. Another thing that's nice about this is that it doesn't just work for extreme Kerr, it works for all extremal black holes, this procedure. Now, of course, one has to look at this for a more modern perspective. So we have since learned that, exactly extremal non-supersymmetric black holes, you cannot really rely on their job. So in order to trust the classical gravity approximation, we should consider instead near extremal black holes. And a lot of the features of this, Kerr CFT business are actually related to near extremal behavior of the black hole, and many of them just captured by a JT gravity model that just has to do with the reduction to 2 dimensions. Okay, so maybe one consider something a bit more general than JT gravity, but that's roughly it. So so this JT gravity model can capture a lot of the physics, but one thing that capture from Kerr CFT is the entropy at extremality. So it can reproduce the entropy above extremality, but not the entropy at extremality. That's the right movers over here. So this is what I'm going to call the Kerr CFT problem. How do I understand? Yeah, so I should define it a bit better. So when I go to the JT gravity description, I want to talk about that S naught and ignore the one loop correction. I was But from the JT gravity perspective, I think if I have a sort of a decoupled perspective, I have a good meaning of entropy, and then I can take a limit. There's a factor in the package book, but I do not call it. I agree that's a sloppy. Okay. But do you have a short correct characterization that you can express in a few words? What do you want to call it? I'm happy. But I mean, in the full description, it should be some sort of entropy. Okay, fine. Okay, we can discuss about it, but besides Alejandra, other people have understood what I mean. Maybe an analogy that's helpful when you look at asymptotically ABS3, you have black holes, you can meaningfully talk about the entropy, go to near extremality, and you have the same issue. So it's analog of the extremal BTZ entropy, but transform to this. Okay. Okay. So basically, what the Kerr CFT problem that's not included in this JTbar, that's not explained by JTbar, is to explain this quantity, and in order to approach it, it's actually better to not work with a very near of the extreme Kerr black hole, because of this focusing of the energies. It's better to go to some sort of toy model where we can have like proper dynamics, a proper decoupled thing. So actually, for me, Kerr CFT from now on will just be warped ADS, which has to do with this factor over here. Okay.
Can I just have to clarify quickly? What I understood that you meant was the part of the entropy that's not linear.
Exactly. Yeah. Okay, very good. So if we're to draw a little diagram of what this bottom-up analysis for Kerr CFT is the following. We seem to, so the isometries of the solution are SL2 left times U1 right. The U1 right gets in right. The entropy sort of looks like Cardi. And then people have also done a scattering calculation. And for correlation functions, you get some CFT-like answer with the conformal dimensions depending on the momentum along this U1 direction. So for people who, I think this should be well known, but basically this comes from, so the people who did the calculation were these people. It's a bit confusing that in the abstract they claim that the scattering amplitude is precise by a dual two-dimensional conformal field theory. But if you actually see what they write down in the paper, so this is the 2D CFT answer, where H right are the dual operator conformal dimensions, and the specific expressions that they have for left and H right actually depend on the momentum along the U1 direction. So basically, the correct interpretation is that you're getting an answer that's CFT-like, but actually non-local. But this non-locality is of a highly constrained form because it does look CFT-like. Okay, so that's the structure. And this whole thing is highly preliminary because, as I said, I don't really want to work in this very near horizon region, and I should, warp the ADS toy model to figure out what's happening. Because one of the things I want is to explain this the entropy. Okay, so I have, there are a lot of toy models to study that are really CFT correspondence, and one can again classify them as and top down. And among the bottom-up models, the most famous are topologically massive gravity and new massive gravity. So these are three-dimensional theories. They're non-unitary, so they have ghosts, so they're not exactly consistent theories. Also, you can have 3D gravity coupled to massive vectors. So all theories have warped ADS solutions, and they're that the warp parameter is determined by the couplings in this Lagrangian. And black hole solutions corresponds to the quotients of global warped ADS. They work. You can also come up with top-down toy models for CFT, and these are consistent truncations of string theory to 3 dimensions. We only know of one properly decoupled background. This horizon geometries of higher dimensional near extreme black holes, so they have maybe a more direct relation to Kerr CFT. And if you look at the 3D they resemble massive vector theories plus a bunch of scalars, but the couplings are very, very finely tuned in this 3D Lagrangian. Fine tuning is such that what happens with the solution is that the warped ADS warp parameter is no longer related to the couplings in the Lagrangian, but it's actually determined by the temperature. So black holes are not quotients. Okay? So the first conclusion that you can draw from here is that there's really no universality for the toy models for warped ADS, unlike for what is assumed of ADS. You can get very different behavior depending on how you choose to model. And in particular, these ones which come from top down, you know, it's I guess hard to cook up an action. You know, couplings are such that they will produce this behavior. Okay, so they're very unusual among all the 3D actions that you could be writing down with warped ADS. Okay, that's one point. Then you can go ahead and study the behaviors, two types of toy models. So the bottom up, by we mean TMG. Okay, so this is what black hole entropy looks like. This is mass, this is angular momentum. The asymptotic symmetry group basically enhances the SL2R isometry of the background to Virasoro left, and the right moving translation to a left moving Kac-Moody. So this is a peculiar thing. This structure, this enhancement structure is called the warped CFT structure. And then central extensions, the U1 Kac-Moody level is negative, so the theory is non-unitary. This is no big, you know, surprise because TMG has ghosts. And then one nice thing about it is that one can show that theories with such enhancement pattern possess some sort of warped modular invariance, and they have a universal entropy. And this universal entropy, this modular invariance, precisely explains this. Okay? And scattering, okay, you get something that depends on the U1 charge. For them, U1 charge is energy, so you get non-local stuff. The top-down models produce very different results. The entropy is Cardy, at least when no additional U1 charges are. The asymptotic symmetry group, depending on what you do, you can get Virasoro left, you can get Virasoro right, you can get both, or if you do something else, you can get the warp of things. So it's really, really inconclusive, and this is lack of knowledge of what boundary conditions to impose is. So I think one cannot conclude anything. Scattering is again consistent with non-locality on the right. Okay, so because of these, you know, these results, so there people, what did I do? People talk about different, at least two different types of dual theories to warped ADS backgrounds. One class is known as warped CFTs, which are putative two-dimensional QFTs, which have this enhancement pattern. SL2 times U1, 2 Virasoro left times Kac-Moody left, these right translations. I say putative, so actually, as far as I know, the only concretely known examples are three. Maybe Alejandra has worked on this, but I don't think there's anything else known. So you have to show that they exist in the interacting case, and they're conjectured holographic ADS. This basically follows from staring at the asymptotic symmetry. Again, depends on the boundary conditions. And in these holographic setups, you tend to get negative level. As you see here, even in string theory, you get negative level. So okay. Non-unitary and non-local. And I should say that the simplest proposed holographic realization of warp CFT is actually just pure AD3 gravity with some boundary conditions called comparison, where you basically make fluctuate the plus component of the boundary metric, and you freeze what would have been, you know, the right moving stress tensor to a constant. And then you can see that the asymptotic symmetries are precisely this Virasoro left times Kac-Moody left with, you know, with the standard Virasoro central charge and the negative level that depends on this L bar. Okay, so that's what's proposed. For the constructions, people sometimes talk about dipole CFTs. This is related to this one non-decoupling limits for warped ADS background. String theory is related to the dipole deformation of the D1, D5 system plus flow to the IR. Completely intractable, so you know You have no idea about the properties of the theory. However, what you get is that this should be some irrelevant deformation of a 2D CFT that leads you into a UV complete theory. That's very, this is what string theory leads to. And this theory naturally local and conformal on the left because you have 1,2 and non-local. Okay. Very good. So this is the current status. So you have some bottom-up approaches. You get something like this, but there are question marks everywhere because we don't know the boundary conditions. And the top-down, you get this idea that this irrelevant flow that gets you into UV complete theory, but it's completely intractable. And what I wanted to point out is that the toy model for your holographic setups is actually important. Have select boundary conditions, so it would be nice to get some additional input into this problem because otherwise we cannot make progress. And the idea is that having some explicit field theory toy model for the correspondence can help. So what is this toy model basically realizes this sort of flow. It's an irrelevant flow out of CFT that gets you into something UV complete. And it's an exactly solvable theory, and because of that, we can just actually compute what all of these things are. And yes.
Since the CFTs are non-unitary.
Which CFT is non-unitary?
Previous ones, you have negative levels, things like that.
So I guess what I'm trying to say is that I'm really not convinced that this theory.
Even worse. Making a comment about this as a flow, can you say things about C theory and things like that if you don't have unitary?
Okay, so this is why. So the non-unitary stuff was on the bottom up. Okay? The non-unitary stuff with the K negative, this is in the bottom up, in topologically massive gravity, all these sick theories that it's not a problem that they're non-unitary because they already had ghosts. On the string theory side, you'd better expect something unitary.
Yeah, but I see a minus there.
Well, this is some particular boundary conditions that were chosen to produce this asymptotic symmetry group. But what I'm trying to say is that you have no clue what the boundaries are, and there exist boundary conditions where you can just get Virasoro with the standard central charge. So I think there's no, so what the boundary conditions produce, warp CFT kind of stuff, they tend to give negative level, they look non-unitary, but it's absolutely not clear whether these are the correct boundary conditions. It's also absolutely not clear whether these are valid toy models for anything that you may be interested in.
Boundary conditions that turn the sign positive?
Yeah, so I think this is not sort of the way to approach. I think you should ask, what are the correct boundary conditions for the system? It's not whether you can engineer, because you don't know whether a consistent theory exists for any sort of boundary condition that you might want to impose, or any toy model that you may want to work with. Okay, good. So this was supposed to be the status. Any questions? No. How much time do I still have? Oh, sorry. Okay, so I must have spoken very fast. Okay, sorry. In the D5 CFT, you can, well, it depends. You can sometimes identify it. So this 1, they're supersymmetric descendants of 1,1 carries. And those are 22 of them in the K3 compactation. And one of them is an holonomy singlet. And that's actually the one that's most closely related to the Myers-Berry black hole, so you can actually identify it throughout the moduli space, from the stone cupping point to the orbifold. The other guys, there's some, they don't mix, it doesn't mix with 1,1 chiral primaries, whereas the other guys can mix with each other. But yeah, you know what it are, but I mean, so there's not a identifying what the guy is over here. The problem is, how are you going to flow in such a way that the remains UV complete. You know, this is very hard.
I was mostly asking that it's clear that it's not a JT deformation.
It's clear that it's not a JT deformation because the JTbar one is actually in the vector of SO21, or some combination of vector and singlet.
I guess you have a gravitational picture of what it looks like.
This is a warped ADS spacetime. So actually, if you go to the IR, it looks like ADS3, and in the UV, it looks like this non-normalizable deformation. Yeah. So this is where it comes from. But in the higher dimensional deformation, you can see explicitly that this deformation is very special. It's very fine and actually preserves UV completeness. That's for deformed n equal to 4 super Young means. For this case, you cannot say anything concrete from the gauge theory picture. Okay, so this is sort of the status. These analyses are sort of ambiguous, and this analysis is sort of untractable. So we want to do a toy model and see what it gives us. The toy model, it's called JTbar deformed two-dimensional CFTs. So what's the JTbar deformation? It's some irrelevant deformation of two-dimensional QFT, which is constructed. So it's an example of a so-called homological deformation, and it's constructed from a bilinear of two conserved currents. So in this case, it's going to be a U1 current, J, and the right moving translations, which is T bar. Okay. So, but more generally, what one does is some antisymmetric combination of the two current components, and then this turns out to actually have a very interesting, when operators together, because of this, the way this combination works, you're going to get some with a constant coefficient, and everything else are going to be total derivative terms. So this defines for the Zamorodnikov operator, which has very nice factorization properties. And then you take it and you add it to the action in sort of incremental fashion. So you add it in the undeformed theory, then you recompense in the deformed one, and you add that operator and so on. And this is actually a formation. You don't need to add anything else. So that's the magic of Smirnov-Zamorodnikov. And people usually study, like, there are two deformations that are like studied. One is JTbar, where you take the two currents to correspond to components of the SER. And the other one is JTbar, which is of interest of me now. And as I said, here one current is a U1, and the other one is the right moving stress test. The deformation, therefore, has dimensions 1, 2, JTbar. Therefore, it breaks Lorentz invariance. It actually preserves LSL2 on the right. So after you add it incrementally to the action, it's going to end up with a theory which is local and conformal on the left and non-local on the right. This is precisely what we are calling a 2D dipole CFT. So it's an example of a 2D dipole CFT. The nice thing about it is that these deformations are argued to be UV, and JTbar is exactly solvable. So we can ask our questions. Okay, so it's solvable. So what about its observables? It turns out that all observables that could be computed are simple, universal, local deformations of the original CFT observables. So the way you do these calculations, most of the time you put the theory on a cylinder of and you look at the flows of states and of energies. And at least in the classical limit, this operator is exactly known. So what do you find? So here I'm writing my favorite observables. What do you find? So for example, you find that so you can derive the exact spectrum, and then from the fact that the deformation is adiabatic, so the number of states really doesn't, you can derive a universal entropy, which takes the Cardi form. So it reduces to Cardi if the U1 charges are 0, but otherwise it's different from it, and it's universal. These are obtained by, you take the Virasoro-Kazmudi generators of the original theory and you flow them. So the algebra is going to stay the same. However, what's special that's happening is that actually this Moody generators are not the natural generators, quasi-local generators that act on the fields in your theory, but they differ from them by like spectral flow by lambda times the right Hamiltonian. So if you want to look at the actual symmetries, their algebra is nonlinear. And this kind of weird realization of Virasoro-Katz-Moody that's actually no locality. You can also do correlation functions. For that, you have to define analogs of primary operators. Turns out they exist, and they're very nice. And you find that their correlation functions are entirely determined by those in the seed CFT. And if you look at 2- and 3-point functions, they look exactly like CFT momentum space correlators, but where the dimensions have been replaced by some momentum-dependent combinations. So it exactly fits with what one was finding for the black holes on the gravity side. It's a different function here, though. Okay, so the black. So it's the same flavor, but I mean, this is double trace. Those guys are single trace, and no, it's but the phenomenon, it's yeah. No, yeah, this is dual to ADS3 with funny boundary conditions. It's not part ADS. Yeah. Okay, good. So now, okay, so we could compute all of this stuff in the field theory directly, very explicitly. And now we wanted to say what it does in how to see all these features. So as it turns out, the holographic dictionary bar deformed CFTs, you can just write it down very simply, because JTbar is a double trace deformation from the holographic perspective, and therefore responds to ADS3 gravity with mixed boundary conditions. Very simple. To model it, you need 3D gravity coupled to 2 Chern-Simons gates. You have both a left and right moving ion current. And then, you can do Haber-Stratonovich to see how the sources, field bind and, gauge field in the deformed theory are related to sources and waves in the undeformed. It's the standard stuff. The punchline being that the boundary conditions bulk fields, which correspond to just fixing this guy and this guy, are entirely determined by the field theory. So from the gravity side, you just write down your model to model correctly what this guy does, and then you're done, and everything is being told to you. And you're just following algorithms for how to compute stuff. And, if you want to write down, if you fix this to be 0, then this is the most general, astically whatever JTbar solution to this. So it's parameterized by 4 functions: L of x plus, J of x plus, L bar of some field-dependent coordinate, and so on. Okay, and one thing to notice is that if we make this L bar to be a constant, the gravity part is identical to the CSS solution of pure. Okay, so now, okay, so one can take these solutions and all the charges, all the entropies, all the blah, 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 you get perfect match to JTbar deformed spectrum. I won't spend time explaining. And then you can also do the symmetries, which are sort of interesting. And so as I said, the symmetry generators are this JTbar flow with the JTbar operator that flows the states, which down exactly. So we can just solve in the classical limit for the flow generators. And then we do this nonlinear redefinition in terms of actual, quasi-local physical generators. This is what they look like. So we have some generators of Virasoro and Katz-Moody left. These are standard. And then for the right-moving guys, they're actually field-dependent coordinate transformations. So you're shifting the right-moving coordinate by the bosonization of the current. Importantly, you have to subtract the 0 mode of this boson. This is what the flow to do. And this is very important in order for the algebra that you get to be with U1 charge quantization. If you don't do it, you get crap. So what we did with Sylvia, we took this and we translated it to the Lagrangian formalism to see what the corresponding transformation looked like. See that for each of the right-moving Virasoro, if you wish, and Katz-Moody, we have to accompany each shift by a large affine transformation. So So one that goes linearly in the coordinate. Again, we can explain with a coefficient that depends on the charge. So these are very equations, but they are necessary in order for the U1 charge quantization to be obeyed. We can understand this in the Lagrangian formalism. Then we can do the asymptotic symmetry. So we take the boundary conditions that were given to us from the field theory. We solve for the most general Diffie and gauge transformations that are compatible. They're parameterized by 4 functions. One important thing, we have to require the gauges to be periodic. That's basically implementing this U1 charge quantization. And this forces some of the functions parameterizing the solutions to have winding. And that winding, when we compute the asymptotic symmetry group, will give rise to nonlinear terms, which precisely reproduce the nonlinear modification of Virasoro-Katz-Moody that we can see from the field theory side. Okay, so we get perfect match to a symmetry algebra field theory. And as I said, all these asymptotic symmetry group calculations are nasty. They're obtained by just doing this, algorithmic Barnish-Brandt formalism. What's important is having the boundary conditions and the quantization condition. That's the field theory input that we use, and then everything works out using the given formalisms. Okay, so the holography part. And maybe I can spend 1 minute commenting on CSS boundary conditions. So as I said, say we set J bar to 0 and we take L bar to be a constant, then the metric reduces to the general comparison-Strominger solution in pure gravity. And a natural question is whether the dual to CSS can be understood as a subsector of this JTbar deformed CFT. And the answer that we find is no. And the reason is because even if in this limit the metric reduces to the CSS metric, the gauge not, and actually the gauge fields contribute to the conserved charges. So we get very different answers for the asymptotic symmetries. Yeah, so what CSS see is just this piece, and this is why they have to fix L bar and get some, state-dependent level and so on. Our charges are the sum of all of these, which are like trivially integrable. So we find a state-independent Katz-Moody level, and everything works nicely. So it's not, one can try to give an interpretation to this. My personal interpretation is that maybe this CSS boundary condition, maybe it's just not a correct toy model. In the sense that if you really want to do some double trace deformation of a CFT by something that only depends on the stress tensor, because if I have a gauge field, then I have to put on coupling in the bulk, then there's no way to write such a thing. So maybe if I really want to implement CSS like boundary conditions at the level of the metric, maybe I really need to turn on the gauge field, and then I get very different answers for what the asymptotic symmetry group is. Sorry, what does this mean? I still have 10 minutes. Okay, very good. Sorry, I was rushing because I thought I'd be out of time. Okay, so one can discuss. I don't have a very full argument, but to me it looks that maybe this is just simply not a good toy model from which to extract these conclusions. Okay, so this being said, okay, what does this precision match between gravity and field theory, what can it teach us about Kerr quote-unquote CFT? Well, so one obvious conjecture that you can make after all of this is that the observables of this Kerr quote-unquote CFT are precisely the JTbar observables. By which I mean, for you should get JTbar modified Cardi, and for the symmetries you should get this funny Virasoro-Katz-Moody that acts in a funny way. And if you remember what I said when I reviewed the Kerr CFT correspondence, what people find currently. And part of the reason is because people weren't really turning on the C1 charges. So maybe if you start going to the theory construction and turn on the C1 charges, maybe you can see whether the Cardi or maybe JTbar modified Cardi. Problem with doing this is that one doesn't really get this warped idea of decoupling limit. So we tried to do it with my student for a really long time, decoupled background, and we didn't get to work. And the other ones are not decoupled, so we don't know where the time is the correct time, and you know. Song and Luis Apollo, they have a proposal for one of these backgrounds where they can get JTbar deformed thermodynamics. It would be nice to argue that this is the correct result, not that you can get it. But one of these backgrounds, they can get this. Question is like, okay, how can we find the correct boundary condition, and then see whether the symmetries look like this or not. And one point that we have tried previously in the relationship between JTbar deformed CFTs and asymptotically linear dilaton background was that if you know exactly how your background depends on the black hole parameters, so if you know exactly your black hole phase space, you can try fixing the asymptotic symmetries, comparing the radial symplectic form between of the metric due to the action of the asymptotic symmetry group parameters on the background, and the variations that take you in between the various black holes to be 0. So this is basically saying this Lie derivative do something in the phase space. This guy, I know that it's in the phase space. Radial symplectic form for two things in the phase space should be 0. That's okay. That's like the symplectic pairing of sources and waves, and here I'm claiming that they're two. So if you do that for the asymptotically linear dilaton background, you find precisely the JTbar asymptotic symmetry group, which again has this type of nonlinear structure. And as far as I hear, so my ex-student was looking into this for the Wei Luis background, and she seems to be finding the JTbar structure. The question is, is this the correct way to be finding functions for your non-ADS holography question? And okay, so this is and question: how do we fix boundary conditions in this non-ADS holography? How do we fix the parameterization of the backgrounds? I'll leave you at that. So to conclude, so what I talked about, so this bottom-up asymptotic symmetry group-based approach is a powerful tool to obtain insights into non-ADS holography. I don't think there's any question about that. In doing so, one has to deal with all sorts of ambiguities, and one must be careful about the choice of gravitational toy models to draw one's conclusions. Therefore, I argue that input from top-down approaches and QFT top models seems necessary to guide these powerful bottom populations. And I gave the Kerr CFT example, and presented some way to maybe proceed that may allow to fix us. But I guess the question that I would like to leave you with is is there any universal rule for how to find the appropriate boundary conditions on a given spacetime in some holographic, non-ADS holography?